The nature of light has intrigued scientists throughout the ages. Today it's used in all sorts of applications, from lasers and communication to particle accelerators. We're living in a science and technology boom period. But the roots of our understanding of optics and light can be traced back to a period between the 9th and 14th centuries. That's when a revolution in science took place in the Islamic world, a golden age of science. I'm Al-Khalili, a British professor of theoretical physics, but born in Baghdad. I'll be looking at the state-of-the-art applications of optics and tracing back their roots to those pioneers in the Islamic world who revolutionized a new understanding of light during the Golden Age. This is Sesame in Jordan. It's a synchrotron, a giant particle accelerator that's going to produce high-energy light for groundbreaking experiments. Now, Sesame stands for Synchrotron Light for Experimental Science and Applications in the Middle East. The light it'll produce will allow us to study the structure of matter with incredible detail, to learn more about, for example, how cancer grows in living cells, or to analyze cracks in concrete to see why bridges fail, or to check for pollution in the soil. This facility is a pioneering collaboration that's bringing together scientists from around the Middle East and neighboring countries to carry out fundamental research that transcends political and cultural differences in a way that hasn't been seen in this part of the world since the Golden Age 1,000 years ago.
The ruling caliphs of the medieval Islamic world brought together scholars from around the globe to further scientific knowledge. Amongst their achievements, they revolutionized the way we think about vision and optics, paving the way for our modern understanding of light. Sesame isn't yet fully operational, but today I've been given exclusive access to this enormous experimental apparatus to see how a synchrotron produces light by using very fast-moving electrons.
Hi, Maher.
Oh, hi, Jim.
Nice to see you.
Nice to see you.
So this is the booster ring?
Yeah, this is the booster synchrotron, which increases energy of electrons so that they can produce synchrotron light.
And where's the electrons produced for the ring?
They are produced in the microtron, it's called.
Okay. So this is where it all begins?
Yeah, this is the microtron, which produces electrons and accelerates them up to specific energy so that they can be injected into the booster. In fact, the electrons are produced from this source, which is electron gun, and they are accelerated by the RF source, which we call the magnetron. It's the same device in the microwaves at home, but with larger power. And when the electrons are accelerated, we can extract them through the transfer line into the booster synchrotron.
And it's in the booster ring that they are accelerated around in a circle faster and faster?
Yeah, to get more energy, so their speed will be almost the speed of light. And then they are injected into the storage ring, where we accumulate the electron beam there in order to produce the synchrotron light.
And that's when you can use the light
exactly
to
for
do
the users.
To do the experiments.
Yeah.
So there are several stages to Sesame.
First, the electrons are produced in the microtron, which accelerates them around. When they're fast enough, they get injected into the booster ring, where they're accelerated even faster. And finally, as they approach the speed of light itself, they're fed into the storage ring. As the electrons are steered around using powerful magnets, they lose energy in the form of light. This is the synchrotron light, which will be used for all sorts of experiments. Even without the synchrotron light, some experiments are already underway at Sesame. Warood Shadid is a scientist who's using infrared light, which is invisible to the human eye, to see the effects of drugs on skin. She's using a special infrared microscope which allows her to determine the chemical composition of samples of skin.
I can see here on your computer screen
Yeah.
what the microscope
Yeah, of course.
can see.
This is the surface of our sample that we are studying. It is a skin sample. If you click at any point you want, you can get the infrared spectra for this point. When you add a drug or treat your sample in any way, these peaks will be different. So you can study what is the effect of your drug on this sample by studying the changes on your infrared spectrum.
Warood's research currently uses its own infrared light source. But once the synchrotron is up and running, she'll be able to do her research at one of the experimental stations that'll be built around the storage ring, and she'll use the synchrotron light.
When we have the beam line, which is from the synchrotron, we will have a light which is very bright. So our sample can be studied with a very high resolution, and so our result will be better.
The experiments that will be carried out here at Sesame will all rely on a precise mathematical understanding of light. And it was the scholars of the medieval Islamic world, as they sought to mathematize science, who first laid the foundations of our understanding of light. Isaac Newton studied here in Cambridge in the 17th century and is regarded by many as the father of optics. But there's another father of optics who goes back much earlier and who's often overlooked. His name was Ibn Al-Haytam. Born in the 10th century, he's probably my favorite scholar of the Golden Age because, like me, he's a physicist.
Born in Basra, Ibn al-Haytham excelled at optics, maths, astronomy, and much more. As a young man, the prodigious Ibn al-Haytham travelled to Cairo. The story goes that he was invited to Egypt after he promised the ruling caliph there that he could stop the Nile from flooding by building a dam. However, he soon realized that this task was technically impossible, and so he feigned madness to escape the caliph's anger and was instead thrown into an asylum. There, he's thought to have written much of his important work, Kitab Al-Manadhir, the Book of Optics, which was hugely influential for centuries. Mehdi al-Haddad is an Iraqi engineer at Cambridge University. Together, we're going to recreate one of Ibn al-Haytham's most famous experiments, the camera obscura.
We found this room for you. Tell us what you think.
Very, very nice. What's the view like?
We have this tower.
Okay, I think that clock tower will be perfect. All we need to do is black out the windows and get the screen in place.
Yep.
The camera obscura is essentially a giant pinhole camera, the size of a room so that we can stand inside it. Although the idea of the camera obscura was known about previously, Ibn al-Haytham's account is the earliest to mathematically explain how it works. He used it as proof that light travels in a straight line.
Okay, I just now need to make a hole. So if you get the screen, right. I'll turn the lights out.
And we'll see if we can
what
see
we
the
get.
tower.
Well, that's quite incredible. It looks like a painting, doesn't it? It almost doesn't look real. And, you know, all we've done is block out the light from a room and then allow it to come through this small hole. That is the clock tower. You can see such detail just from across
You can even see the
yard.
trees.
Yeah, they're not in focus because, you know, you could make them in focus if you made the hole smaller.
Right.
But of course, then less light can get in,
That's right.
so it wouldn't be so bright. Whereas now you see it in all these, the vivid colours, and it's so simple. I mean, Ibn al-Haytham would have set up an experiment like this in a darkened room. Such a simple thing to create without any lenses or modern equipment. You know, 1,000 years ago, for him to have explained how this image is created through the hole, and must make you proud as an Iraqi who comes from just down the road from where Ibn al-Haytham was born.
That is exactly it. I'm from from an area very close to where Ibn Al-Haytam was born, so it makes me proud.
Ibn al-Haytham's explanation of the camera obscura helped us understand how vision works. The eye is itself a camera obscura. And the same principles apply to modern photography. After all, that's where the word camera comes from.
I'm going to Istanbul, to the Museum of the History of Science and Technology in Islam. Zeynep Kulaili has been studying Ibn al-Haytham's work, including his explanation for why the camera obscura makes an image that's upside down.
He's well regarded as the first scientist to correctly explain the camera obscura. Talk me through how this works.
If you press the button there, this is the primary light source, and this is the object lighted by this light. The light has to go into the box through this pinhole. You see the F here, and if you look at from here, you will see that the F is converted. It is upside down.
Yes, that's because the light from the top passes through the hole and ends up at the bottom, and they cross over.
Crossover, because light takes the shortest way and it travels in straight lines.
And this was something that he was able to show and prove.
The fact that light travels in straight lines was known before him, but he, for the first time, proved it mathematically.
Ibn al-Haytham's Kitab Al-Manadhir is often cited alongside Isaac Newton's Principia Mathematica as one of the greatest textbooks in physics ever written. Latin translations of it influenced such men as Da Vinci, Galileo, Descartes, among others. Such is his fame, today he is commemorated on the back of an Iraqi 10,000 dinar banknote. He's probably most famous for being the man who explained how vision works. Until then, the accepted view had been that of the ancient Greeks, men like Plato and Euclid, who argued that the way we see objects is by shining light out of our eyes onto them. Ibn al-Haytham knew of this view from Arabic translations of Greek texts, but he challenged it, arguing instead, correctly, that the way we see is by light entering our eyes from outside, either reflecting off objects or directly from luminous bodies like candles or the sun. What was most impressive about Ibn al-Haytham is that he combined theory and experiment. So not only would he devise careful experiments to demonstrate particular ideas like light traveling in a straight line, he also put mathematical flesh to these ideas. He mathematized whole fields of science.
Professor Stephen Sweeney is a colleague of mine at the University of Surrey. He works at the cutting edge of laser physics today.
In the medieval world, there's one scholar in particular that I'm passionate about, Ibn al-Haytham, and he wrote a book of optics 1,000 years ago in which he was doing all those sorts of things that you associate with experiments with light today, so reflection and refraction of light, even down to designing experiments with camera obscuras to prove that light travels in straight lines.
Those aspects of understanding the properties of light are absolutely key to modern science and technology, actually. But perhaps the idea that light travels in a straight line is one of the most important ones, and it's one that we really now make use of in technology and science. And actually, we've got a nice example of that here that I can show you today, just based on the research we're doing right now. We're going to be using a laser, and we need to wear these just to protect our eyes for the experiment. Okay, so what we've got now is there's a beam of light, an invisible beam of light, travelling a nice straight line from this laser down to this detector at the other end. Now, if I put this card in the way, you can see that there's a nice spot, nice red spot. When I take that away, the light's travelling through and it's hitting this piece of material here, that's called a photovoltaic cell. So you've heard about solar cells for collecting sunlight. This is a particular type of photovoltaic cell for collecting laser light. And it's actually then driving this little motor, so it's just a little fan. So if I block that again,
It stops.
You see it stops. And if I pull that away, you can see the fan starts again. Okay? So it's another way of transmitting energy, essentially. So not using electricity, but using light itself as the medium.
And what sort of applications might this device, this setup have?
One of the key projects that we're interested in at the moment is transmitting energy from space, because in the infrared we can actually get straight through the atmosphere without losing energy. We used a system like this in space. We could transmit solar power 24 hours a day anywhere on the planet that we need it.
This has huge implications the world over in terms of producing power. We wouldn't need pylons and power lines, yet power could be delivered to remote areas or disaster zones. And this technology also has implications for the internet.
We obviously use the internet for data transmission. That uses infrared light, actually. But if we also put in some sort of high power component to that, we can also deliver the energy. So we can actually deliver the power signal for the internet as well.
And this light, you say it's infrared. So if I put my hand there, I don't see it.
No.
I can sort of, am I imagining I can feel warmth?
You're probably imagining it, because although it's infrared light, it's not quite far enough into the infrared to be measured as heat. The reason we use infrared light is purely because it's a better way of transmitting that light through the atmosphere. And actually more than 99% of the energy can transfer through the air. Now, in the real application that we would use this for, we'd actually use an even further infrared laser, and that would allow us to then not have to wear these safety goggles. So it's what we call an eye-safe wavelength.
I'm sort of wondering what Ibn Al-Haytham would think doing experiments with candles and pinhole cameras. Well, he wouldn't even be able to imagine a world 1,000 years later.
I think it's come a long way, but ultimately we're using exactly the same principles that he was thinking about back then.
Today, we understand the physics of how light behaves.
But back in Ibn Al-Haytham's day, this wasn't at all obvious. His book changed everything, and he's regarded by many as being the father of modern optics. In fact, I'd go further than that and say he was the greatest physicist in the 2,000-year span between Archimedes and Isaac Newton. So many modern cities around the world today are lit up spectacularly by light. It seems the applications of optics are everywhere. Have a look at this beautiful fountain behind me. It looks as though the coloured beams of light are bending round following the paths of the water. However, that's an optical illusion. Light, in fact, is shining up from the base of the fountain and then reflecting off the water droplets into our eyes. Light always travels in straight lines. However, there is a way that light can be made to bend. If I shine this laser pen through this glass of water, if you look carefully, you can see that the beam of light bends as it enters the glass and the water. This is something that every physicist knows as Snell's law of refraction, but it was known many centuries earlier. Let me show you this rather remarkable diagram. It's from a text that was discovered only 20 years ago, partly in Tehran and partly in Damascus. It's by a little-known scholar by the name of Ibn Sahel, and it describes Snell's law of refraction beautifully. Let me explain. This line represents the boundary between air and water. If a beam of light enters the water at an angle, it will refract, it bends towards the vertical. This angle is larger than this one. If I draw a circle around it, the ancient Greeks understood that this angle of incidence, the angle that the beam enters through the air, is larger than the angle of refraction in the water. But they knew that the ratio of the two angles remains constant. If you double this angle, that angle doubles. The way they described it was in terms of the ratio of these two parts of the circle's perimeter. That was wrong. What Ibn Sahel understood was that it was in fact the ratio of two straight lines. He said that this chord divided by this chord is always a constant number. This is the correct way we understand it today. Now, Europeans argued about whether it was Snell or Descartes who should be given credit
for the law of refraction. In fact, it was discovered by Ibn Sahel 650 years earlier. So really, it should be known as Ibn Sahel's law of refraction.
Another little-known scholar from the Golden Age who fascinates me is a man called Ibn Mu'adh, who in the 11th century came up with one of the earliest estimates of the height of the atmosphere. Now, he'd worked out that after the sun sets, the last remaining daylight comes from light reflected off the upper edges of the atmosphere. He figured out that this would take place when the sun was 19 degrees below the horizon.
Imagine that I'm standing on the surface of the Earth at this point, A. The sun has gone 19 degrees below the horizon. Above me is the atmosphere, and I can see the last light of the day reflected from the top of the atmosphere at B. We can draw this triangle to the center of the Earth at O. Knowing the size of the Earth, calculated by the astronomers of Baghdad in the 9th century, Ibn Mu'adh was able to use geometry to work out that the atmosphere was about 80 kilometers high. That's not bad for almost 1,000 years ago. Throughout the Golden Age, Ibn Sahel, Ibn Mu'adh, and many other scholars wrote detailed texts on optics. But none were so comprehensive and influential as Ibn Al-Haytham's Kitab Al-Manadhir. At the Suleymaniye Library in Istanbul, Professor Ramazan Sheshen shows me an ancient copy of Ibn Al-Haytham's great work.
ما هو هذا الكتاب؟
هذا ابن الهيثم كتاب المناظر
هذا كتاب المناظر.
Optik.
The Book of Optics. Wow. Of course, this isn't an original copy. This was written in the mid-15th century for Sultan Muhammad, who founded the Ottoman Empire. It was written for his library. هذا الموضوع يعني
يصور عدسة يعني
عدسة نعم.
كيف يأتي الشعاع كيف ينعكس في العين يعني.
For me, what's so amazing is that we, all around the world, we talk about Newton as being the father of optics, and yet here we are, 1,000 years ago, 700 years before Newton, and here's a ray diagram. There's a convex lens, and there's a focal point, and there's all the ray lines and parallel lines and the angles of refraction. Here it is, 1,000 years ago. Optics are all around us, from the glasses or contact lenses you wear, to the screen you're watching me on right now, to the particles of light produced in a synchrotron. Everything we know about optics today is built upon the work of scholars like Ibn Sahel, Ibn Mu'adh, and the father of modern optics, Ibn Al-Haytam, who first opened our eyes to the science of light. Next time, I'll be taking a look at modern-day astronomy and navigation and exploring the contribution made to these fields by the scientists of the Golden Age. That's where Tusi's genius comes in, because this diagram, the Tusi couple, simplified a lot of that complicated maths.
We see the role they played in the evolution of astronomy.
These scholars had to develop an area of mathematics called spherical geometry, which was exceptionally advanced for 1,000 years ago.
And we reveal how
Scholars from the Islamic world consolidated and refined the astronomy of earlier civilizations and came up with ideas that have deeply influenced astronomy right through to the present day. Copernicus owes this debt to these medieval astronomers from the Golden Age.